Good morning, everyone. I'm Yogadharani, working as Assistant Professor in Department of Computer Science and Engineering at SNS College of Technology. Today, we are going to discuss evaluation matrices, an important concept in deep learning and machine learning. Whenever we build a machine language model, simply training it is not enough. We need to measure how well it performs. Evaluation matrices helps us to understand whether the model is giving correct predictions or whether it can be trusted in real world applications. So this topic is a part of structuring machine learning project, because choosing the right evaluation matrices is essential for building effective AI systems. By the end of this session, you will understand what evaluation matrices are, why they are important, different types of evaluation matrices, and how to choose the right metric. So in this slide, uh, before getting to the topic, we must recap the previous sessions. That is model performance, predictions versus actual values, classification and regressions. So before learning evaluation matrices, let us quick recap what we studied earlier. So in machine learning, after training a model, it generates predictions. These predictions must be compared with the actual values. Mm, and there are two types of ML problems, are classifications and regression. The output in classification, the output belongs to categories. Example, disease or no disease, found or not found. Mail should be in a stay in a inbox, or it goes in a what is that, spam, or other label. So regression is here the output is continuous. Example, predicting house price, temperature prediction, stock price prediction likewise. Here, how to measure model perform, how to identify errors, and then how to compare with other matrices like other multiple models, and how to select best performing model. In short, evaluation matrices is like a report card for machine learning models. Here, mm, let us understand this with a real world example. Imagine a medical diagnosis system that detects cancer. Suppose out of 100 patients, 95 are healthier, and 5 have cancer. So if the model predicts all 100 patients as healthy, it gets 95 prediction correct. Accurate because becomes 95 percentage. That sounds excellent, but the model failed to identify all 5 cancer patients. That is extremely dangerous, and this example teaches an important lesson. How accuracy does not always mean a good model. We must better evaluation matrices depending on the problem. Let us emphasize this one is evaluation matrices are quietly quantitative measures used to assess the performance of machine learning models. They help us answer questions like, is the model accurate, is it reliable, and is it making costly mistakes without proper evaluation, wrong business decisions. A recommendation system may suggest irrelevant products, and misleading performance results, unsafe real world outcomes. Here, ideate to evaluate most efficiently. We can different approaches like use accuracy alone. Here, this is simple but not always reliable. And analyze confusion matrix. This shows detailed prediction results, and then apply multiple matrices. Here we using precision recall, and an F1 square gives deeper insights. And then problem specific evaluation. Here different problems need different matrices. For example, medical diagnosis recall may be used, and then email detection precision may be used. For a balanced task, accuracy is the mainly matter. The most efficient solution is use appropriate evaluation matrices based on the problem. Here, this slide introduces the main evaluation matrices will be discussed here. Accuracy, precision, recall, F1 square, ROC curve, and AUC and confusion matrices. Here, here each matrix performs from a different angle. No single matrix is best for every problem. Choose the correct matrix depends on a dataset type, class balance, business objective, and cost of errors. Here, why evaluation matrices? First one, compare models. If we build multiple models, matrices helps us identify the best one and then detect overfitting. A model may perform very well on training data but poorly on unseen data. Here, matrices reveal this issue. And then measure generalization. Here, good models should perform well on unseen data. Evaluation matrices test this capability. Next, improve decision making. Here, matrices help organizations make informed decisions about deploying models. Here, what is confusion matrix? Here, confusion matrix is one of the most important evaluation tools. It contains 4 outcomes, which comes true positive, true negative, false positive, and false negative. Here, model predicts fast positive and it's actually positive. Example, correctly detecting diseases. And then true negative. Model predicts negative and it is actually negative. Example, correctly identify the healthy patients. And then false positive. Here, model predicts positive but actually negative. Example, healthier patient makes us marked as diseased. And then false negative. Here, model predicts negative but it actually positive. Example, diseased patient marked as healthy. This is often the most dangerous error. Here, confusion matrix is the foundation for calculating many matrices. And here, accuracy. Overall correctness. Accuracy measures the percentage of correct predictions. And here formula is true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. And here the limitation here is it is not suitable for a imbalanced data set, and this is why relying only on accuracy can be misleading. And then precision. Here precision tells us out of all predicted positive how many are actually positive. So the formula becomes true positive by true positive plus false positive. Here it mainly used for email detection, fraud detection, and then legal document classification. And then recall. Here recall teaches out of all actual positives how many were correctly identified. Here the formula for recall is true positive by true positive plus false negative. Um, Here example for cancer detection, intrusive detection, and then disaster warning system. And the next matrix is F1 score. Here F1 score combines precision and recall. That is here formula here is F1 is equal to 2 into precision into recall and divide by precision plus recall. Here example is if precision is high but recall is low, F1 becomes lower. This ensures balance evaluation. And the next metric is ROC and AUC curve. It plots true positive rate against false positive rate. It slows model performs across different thresholds. Here AUC stands for area under the curve. Here ROC and AUC is very useful for comparing classification models. And this slide shows the summary of evaluation matrices. And this is the mind map for evaluation matrices. So, a successful machine learning project depends not only on building models but also on evaluating them correctly. So, before deployment, ask what kind of error matters most, and is the dataset balanced, which metric matches business goals, and smart evaluation leads to better models. Thank you. Catch you in another video.